All right, so there was a time not all that long ago when we didn't have lights at night, right? Other than inside our house. We didn't have a lot of light pollution, and so people could see a lot more of the sky, or they could see many more stars. So we're going to start talking about the celestial sphere. We're going to talk about what causes the seasons. We're going to talk about what causes eclipse, right? We're going to kind of go through all that really quickly today so that you get beginning of an understanding of this aspect of being on the earth. Okay? You guys all recognize this, right? Stonehenge. Stonehenge was created for a particular purpose, and we'll get to that in a bit. So, when you look out at the stars, can you tell how far away they are? Yeah. Right? They're so far away, they all look like they're really at the same distance. So, the first theory, if you will, of the stars, where they all sat on a shell somewhere out there that we called the celestial sphere. And they were all just points of light on this celestial sphere. Well, we know not only they're not all at the same distance, right? But not all of them are stars. Some of them are galaxies. Right? Some of them are galaxies. One of the things I hope to be able to do in lab this semester is for us to see the Andromeda galaxy. The only reason you don't see the Andromeda galaxy is because it's so faint. It is 3 million light years away, and that makes it very faint. Now we see as a star the center of the galaxy, but we don't see the whole galaxy, which is actually about 6 times as large as the moon in the sky. It's just too faint for us to see. All right. So one of the things people did sitting around bored with nothing else to do at night, staring up at the skies, was they drew pictures around the stars to say, oh, this looks like a lion. This looks like a scorpion. This looks like, a couple of kids playing, right? Now, we have a set of, if you will, constellations in our culture that we talk about all the time. How many of you know your astrological sign? All right? I'm a Leo. You know your astrological sign corresponds to a constellation. Right? So there are these 12 constellations in our culture. The Chinese have different constellations. The Jews had different constellations. The Aboriginals had different constellations. You're saying, can you take the same set of stars and draw different pictures? Right? And that's what everybody did. And so they had, instead of using, instead of looking at this and saying, oh, there's Lion, there's Leo, they might say, oh, these stars go with some more over here, and these go with some over there, right? Completely different constellation. And even in our culture, there are a bunch more constellations that we just never talk about because they're not the ones that rotate that as noticeably along the same path that the sun follows through the sky. The 12 constellations that we talk about follow the path of the sun through the sky. All right. All of you know, I hope, that the Earth is tilted with respect to its orbit around the sun. All right? So, if you imagine the Earth spinning like this and going around the sun, it doesn't do it like that. The Earth is like this and goes around the sun like that. All right? So the axis of the Earth always points in the same direction, even though it's going around the sun.
Doesn't it tilt over like the season? Doesn't it tilt a different way over the season?
Tilts the same way, and that causes the seasons. All right? We'll get to that in just a minute. So the Earth is spinning, right? The Earth is spinning. The sun doesn't come up, right? The sun does not rise. So if you imagine you were an ant sitting on this, and as it spins, right, you would see the projector rise in the east, right? And as it keeps spinning, you would see the projector set in the west, right? The sun's not actually moving, we are. Does that make sense? It's like being in a car. When you're in a car and the trees are going past you, do you say, oh, look how fast the trees are going? No, trees aren't moving, right? You're moving. So that's why it looks like the sun rises, because we're headed that direction, right? And then it sets because we're headed away from it. And we just go around and around and around, and we see the sun come up because we're headed that way at a pretty rapid clip. Okay? The reason, here, let's do this real quick. There's something called conservation momentum. That is the reason that the sun always points, and that the earth always points in the same direction. Now, that's a little bit of a lie. The direction the earth points in actually goes in a circle. But it goes in a circle over 22,000 years. So for practical purposes, you know, in our lifetime, it's always going to point in the same direction. The reason it does that is a little something called conservation of momentum. There we go. So if I take this, and I hold it up by one end, and I let go of the other, what's going to happen?
It's gonna fall.
It's going to fall. Right? So, here, be pretty strong. Pull as hard as you can. Right? Conservation of angular momentum. Because of conservation of angular momentum, the earth stays pointing in the same way, the same direction all the time. There are forces on it, right? Not as big as gravity on this. So over 22,000 years, it does rotate around just like this rotated around. But it rotates around staying at that 23.5 degrees. Right? So we could actually draw a little circle in the sky that is the circle that the pole of the earth points at over those 22,000 years. The conservation of angular momentum is why the earth always points in the same direction. Now, the reason the constellations that we talk about are in the plane that the sun is in. Right? So we got the plane of the sun, we got the earth going around the sun. Right? So when the earth is over here, you can't see the constellation that's on the other side of the sun. Right? Because the only time it's up is during the day, and it's behind the sun, you can't see it. And so the earth then moves a little bit, that one becomes visible, and you can't see this one. So the constellations over the seasons, as we go around, right, as we go around the sun, the constellations we can see drift, they change. We have 12 constellations, we have 12 months, it's not an accident, right? They help us keep up with the seasons, at where we are with respect to the sun. And if you look, if you were to look in the night sky, here in August, right, you would see Leo just above the horizon. That's why people born in August are Leos. Or in June, you'd see Gemini. Right? So as the months progress, which constellation is sitting right there, right after sunset, changes. The other big important thing we get from our, well, that's supposed to be in each hemisphere, we get from the tilt is if I take a ball and I tilt it like this, and a light is shining on it from over here, right? The light's not shining as brightly up here as it is down here. We'll talk about that more in a minute, right? So, in each hemisphere, we have 4 important dates. 4 important dates that people have known about for a long time. These dates are why things like Stonehenge were built, right? To mark them, so you would know we've hit this date. They are the winter solstice, the spring equinox, the summer solstice, and the fall equinox. What are they? So the winter solstice is the shortest day in the winter. Now down here being this far south, I've lived much farther north than this. Down here, you don't notice this as much, but you do notice it. When I moved from Mississippi to Syracuse, New York, my first winter there, I was kind of shocked because come midwinter, you go to work in the dark and you go home in the dark, and the sun is up only while you're at work. Because the sun's not up for a long time, right? The days get really short. And if you go far enough north, again, the Earth is tilted at 23.5 degrees. So once I take this and I rotate it over to 23.5 degrees, there comes a point where, right up here, where everything from here to the pole is in shadow, right? Imagine the sun's over there shining this way. If this is the pole, and I rotate it to 23.5 degrees, then everything from here to here is in shadow all day long. All right? This is the Arctic Circle.
Don't they have like 30 days of night?
Yeah. Above the Arctic Circle, you hit a point where it just stays dark. And then you hit a day when, if you're at the right point, the sun makes a circle around you. And you get to watch it go in a circle in the sky.
So it's the day, the whole day.
The day is the whole day. Right? So when you get to where, amen, the earth is, the sun's over there at first, now we go around, and now the sun's over there, right? You're looking at the sun all day long. Doesn't matter how you rotate, right? You're getting sunlight all day long. The spring equinox. Spring equinox is when, with the sun, the earth like this, is when the sun would be over here, right? And it's shining straight at the equator, and the equator is rotating past. So at the spring equinox, day and night are exactly equal. Then we have the one most people really prefer, summer solstice. It's the longest day. And then fall equinox. Now, if you're from the southern hemisphere, the winter solstice here is the summer solstice there.
Yeah, I remember spending Christmas on the beach.
Yep, that's right. Winter solstice here is summer solstice in the southern hemisphere. Spring equinox here is fall equinox in the southern hemisphere. They're just reversed. Right? So why is it summer here when it is summer here? Okay? It's because the Earth's pole is pointed more towards the sun in the northern hemisphere when it's summer here. What does that mean? That means the light falls more directly on us than in the winter when the light is falling at an angle. If I hold my hand under this light here, right? Am I getting more light on my hand when I'm straight under it or when I'm over here? Right? I'm getting more light on my hand when I'm straight under it. Not only am I getting more light on my hand when the sun is more direct, but the days are longer. So I'm getting more light per minute, and I'm getting more minutes of light. That's why we have summer. And then the other side, when we're not getting direct sunlight, not only we're not getting as much sun per square meter per minute, we're also not having as many minutes in the day. Now the way the dynamics works is this is the longest day, which is when we've hit the point where we're maximally heating the atmosphere where we are. But it takes a while for all this to build up, so it's actually after the summer solstice that we hit our hottest part of the year. And it's after the winter solstice that we hit our coldest part of the year. The reason people, Stonehenge was not a trivial thing to build, right? I mean, can you imagine us trying to take bits of stone that big, A, cut them, B, haul them a long way, and C, set them up so that when the winter solstice came, it would shine through the keystone onto an exact point, and we now knew the winter solstice was here. That's a lot of work, right? It's a lot of work. A lot of different cultures did something similar, not necessarily on that scale. They did something similar because if you mark this, then you begin to know when this is going to be, then you begin to know when to do what? Then you begin to know when to plant. Right? You can begin planning on, we now know when we need to plant crops. We now know when we need to harvest crops. Well, harvesting is a little more, when they're ready is when you harvest. But you now have the pace of the years. You've got something that tells you the new year has started. I call it the new year. You know, it's December 21st, but you know, as far as the earth is concerned, it's the beginning of the next year, so I can with it. All right. That's when we've reached our shortest day, December 21st, June 21st, in this hemisphere. And this is in March, and that's in September. If you look, we're tilted at 23.5 degrees. What does that mean? That means when the North Pole is the most towards the sunlight is going to be direct on the Earth right here at 23.5 degrees above the equator. In the northern hemisphere, that's called the Tropic of Cancer. And the southern hemisphere is called the Tropic of Capricorn. These names are not accidents, in that if we look back here and we say, all right, so I'm hitting my solstice, right? So I'm going to be about here, a little bit further along than they show here. The constellation that's going to be in the night sky right after sunset is Cancer. And then I'm around on the other side, at the other half of the year, the constellation that's going to be just above the horizon at sunset is Capricornus. So we have the Tropic of Cancer and the Tropic of Capricorn.
Is that because you can't see them? Is that because you can't see them?
It's because they're just visible.
All right.
That's when they're just visible. And between these two lines, Tropic of Cancer and Tropic of Capricorn, we have what we call the tropics. All right? We call them the tropics because they have a lot of sunlight all year long. That's why they're hotter. That's why they have more vegetation, right? All of this. That's why they're the tropics. This is an illustration of what it means to have winter sun versus summer sun. Right? If you ever get the chance to move far north, you'll see the sun kind of comes up and goes across like that and goes down. Okay? You don't think of it in the winter, it doesn't do this. If you pay attention here, in the winter it doesn't do this. In the winter it's doing something like that. You look to the south and you'll see where the sun is. If you're in the southern hemisphere, you look to the north to see where the sun is. You go far enough north, the sun gets very low on the horizon and stays there.
Even over the sun is. In the north, would the sun still be like
Yeah.
a good distance?
Yeah. It doesn't get very high even over the summer. All right. So, we're going to move on to the moon. Much like our seasons depend on how we're facing the sun, right? The phases of the moon depend on where it is in relationship to the sun and us. So if I hold up this book and hold it between me and the light, this side of it is dark, right? If I hold it over here, this side of it is light. And that's what's happening with the moon. When the moon is big and bright, it's on the opposite side of the earth from the sun. And when the moon gets dark, it's on the same side of the earth as the sun. Now, when the moon gets dark, have you noticed you still see it? Why do you think you still see it when the moon is dark?
Because of the light projecting the sun.
The sunlight reflects off of the earth and onto the moon. Right? So even when the moon is at full dark, you still see it because the earth is actually a really bright planet. The earth is one of the brightest planets in our solar system because it reflects a lot of light. Because it's a bright planet, it reflects sunlight back onto the moon. Now, why do people say there's a dark side of the moon? What does the dark side of the moon read? All right, Pink Floyd fans. Yes, there's a dark side of the moon. But other than Pink Floyd fans, why do people say there's a dark side of the moon? What does the moon do? Why does it not look like the moon rotates? Have you ever seen the moon change other than the phases? Right? You look up at the moon, you see the man in the moon. Right? So, the moon goes around the earth, and depending on how you count, about 27 to 29 days, but we'll call it 27 right now. Goes around the earth. The moon rotates at exactly the same rate. The result is, as the moon rotates, right? Let me use this. As this goes past me, it's rotating. Right? It's rotating. It's rotating at exactly the same rate that it's going around me. Right? Does that make sense? It's rotating at exactly the same rate it's going around me. Because if it wasn't rotating, it'd do this. Right? That's not rotating. Because it's facing, the part of it facing you is the same the whole time. While you're sitting still and it's going around. The moon does this. We see the same side of it all the time because the moon is rotating at just the right rate to keep the same side facing us.
Is that because like the pull from the earth like pulls it in that tight and then rotates
So it's
it?
related to that. The moon used to rotate with respect to Earth so that its side would change. And used to, by used to I mean a couple billion years ago, right? But what happened was tidal forces on the moon caused, because of friction and tidal forces and rock shifting and everything else, the moon slowly slowed down and went a little farther away. Now, they both go together. As it slowed down, it had to go a little further away. And eventually it became what's called tidally locked, so that the same side faces us the whole time. Give us another 5 billion years, if we get that much, right? And the Earth will be tidally locked to the moon. And the Earth and the moon will, the same point on the Earth and the moon will always face each other. So we can have wars about whether or not the moon exists, right? Because people on half the Earth will see it, people on the other half won't. So eventually, a very long time away, that will happen too. There are other moons out there around some of the larger planets that are tidally locked, so they always face their planet. So, here's a question for you. The moon is going around the Earth, right? And the sun's over here. How often should we have an eclipse? Once a month, right? If it were that simple, right? But, and remember, the Earth is tilted. And because the Earth is tilted, when the moon is between the Earth and the sun, it's actually up here most of the time, or down here, right? And out of the line between the Earth and the sun. And it's only when things work out so that it can come in between that you get the eclipse. There are two types of eclipses. What kind of two types of eclipses do we have? Solar and lunar. Right. Solar and, yeah, I don't need to forget this. This is a GIF that NASA put together. These are photos taken by an observatory NASA stuck out 1 million miles away from the Earth. These are actual photos put together of the moon going past between the observatory and the Earth. Right. So what you're seeing here, you're seeing the side of the moon we normally don't see, so it doesn't look as familiar, right? Because it's not the part we see. And you can see it go past the Earth. And right here, you can see where the sun is shining off of the Earth the brightest. Right. It's from 1 million miles away. About 4 times as far away as the moon. And this is their global weather observer that they have out there to try and map weather patterns on a slightly larger scale. A friend of mine picked out a friend of mine who sent this to me. I said, she's from New Zealand. She's in New Zealand. And I said, you sent it because you can almost imagine New Zealand under the clouds here at the very end. Right? It's right down in there. Almost imagine seeing New Zealand.
You can't see Australia.
You can see Australia, yeah. All right. So eclipses. If the moon and the Earth, if the moon was orbiting the Earth in the same plane that the Earth orbits the sun, we would have a solar eclipse and a lunar eclipse every month. You know, it'd be boom, 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 boom. But we don't because they're at an angle, so the moon's doing this. When we have a solar eclipse, we have the happenstance that the moon and the sun, if you were to hold up your fingers and say, okay, this is how big the moon is when I'm looking at it, and you were to do that with the sun with the right eye protection, so you could actually do it more than once, right? And say this is how big the sun is. The moon and the sun are the same angular size. Now, the sun is thousands of times bigger than the moon, but the moon is so much closer, right? So the moon and the sun look the same size in the sky, which is why when we have an eclipse, it looks like this. Right? The moon exactly covers the sun. Now, we have, you could call it an eclipse. Sometimes Mercury eclipses the sun. All right? Mercury is the planet closest to the sun. There will be Mercury will transit the sun with respect to our view of the sun next summer, but Mercury is so close to the sun, right, that winds up being a little bitty set of little black dots as it goes across the sun. It doesn't come very close to actually covering the sun. The moon is just the right size at just the right distance to cover the sun. Then we have lunar eclipses. On a lunar eclipse, the Earth comes between the sun and the moon. These happen more often. And they happen more often because the Earth is a good bit bigger than the moon. And so it's much easier for the moon to get into the Earth's shadow. When you see it like this, why do you think the moon is red? In the middle of a lunar eclipse, the moon turns deep orangish red. What's happening? So what happens at sunset? Sky turns red. You know why the sky turns red at sunset?
Is the dark and the light are meeting?
No. The Earth's atmosphere bends the red light, so you see the red light longer than you do the other colors. Right? And so what's happening here is the moon goes behind the sun, is the sunset is wrapping around the Earth and shining on the moon. Right? You don't get quite true darkness behind the Earth because the sunset wraps around and shines out dark, deep red behind the Earth.
So when it's red, it's lunar? So
Well, when the Earth goes between the sun and the moon, or it's a lunar eclipse, right? The moon is eclipse. And it turns this dark, deep red. It's very pretty. If you ever get the chance. These are fairly often. I asked, there's a solar eclipse. I asked if we could get money for it. He said no. There's a solar eclipse coming up. Unfortunately, it's in Antarctica. So it costs a few $100,000 to get us all there. Yeah. It'd be interesting. I mean, that's right, yeah. You know, field trip, right? Field trip. We just need planes, trains, automobiles, boats, you know, icebreakers, yeah, snowmobiles.
The other part of that would be getting students to actually go to Antarctica.
Well, there'd be that too. It's a good diet plan though, because if you go to Antarctica during the winter, if you're not eating about 9,500 calories a day, you're losing weight.
I eat that in the city.
What's that?
I eat that in the city.
9,500 calories?
Oh, 9,500?
9,500. Yeah, that's a lot of
I just said
calories.
950.
No, 9,500. The people that work the Antarctic station have to eat about 9,500 calories a day just to keep from losing weight. Because so much of their calories go into keeping them warm. All right. What else do we have? Oh, excellent. We have some time left. Questions, comments, thoughts? No, nothing. Zero. You guys all ready?
What are we needing for lab?
So, section 1, lab is at 6:30 in Kaler 243.
Which is
Okay.
the sun.
Science book. Section 2, lab is at 7:30 in Kaler 243. So here at the beginning of the semester, well, today's lab, we're going to be talking about a do-it-yourself lab. We're going to talk about the homework some, right? We may look at, we may think about looking at problems. We got time. We'll think about looking at some problems today during class. All right, so we're going to do some more here. So if you notice, you will notice, I hope, when you come into lab today, it is not yet dark. Right? And so, the beginning of the semester, you know, we could, if you wanted, look at the stars, but you would need to come around about 11 or 5 in the morning. You know, I sort of thought we wouldn't do that. Yeah. The other thing you'll find in lab tonight, the adjunct, Miss Ann Huber, is going to be meeting with you tonight at lab 3. Okay? So she'll go over the do-it-yourself lab you are going to do for the month of September, which is, in the month of September, you're going to be doing this. You're going to be following the moon across the sky for the month of September, right? So we'll have a lab sheet for you on that. Other questions? Questions on homework problems? Any luck at all with homework problems?
We didn't really understand like number 3.
So which number 3 did you have?
The one with
The quad? Okay. All right, so I have a, all right, let's start bringing a pen. Ooh. All right, so I'll try to explain it without, since I don't have one. This pen is, let's call it 15 centimeters long, right? So if I said you need to draw this pen, but I want you to draw this pen so that 1 centimeter equals, 1 centimeter on the paper equals an inch, right? Could you do that? Let me not change units. So let's say I wanted you to draw this pen, but I want to draw wanted you to draw this pen so that 1 centimeter on the paper equals 2 centimeters in real life. So how long would you draw the pen?
15 centimeters.
Well, it's 50. Let's say it's 15 centimeters now, but you want 1 centimeter on the paper to equal 2 centimeters on
So you
in real life,
so
right? So it'd be half the length, right? Be half the length on paper. Does that make sense? It'd be 7.5 centimeters. So it's 15 now. I want you to draw it at so that 2 centimeters in real life is 1 centimeter on the paper. Right? So 2 centimeters in real life being 1 centimeter on the paper means you divide all the lengths by 2. Right?
How are you supposed to relate this water to that? Don't get us later.
So the question is, how big is the solar system? Now we're going to take this, we're going to make it the length of the solar system. Right? And here are these letters on here. Right? I'm going to say this is the length of the solar system. And I want you to go out to the quad, and I want you to draw those letters so that as if this pen were just the length of the quad. How big would those letters be? And where would they be? So if, let's say, the letter, let's just take this band. Can everybody see this black band? Right? Suppose I just ask, where is this black band on the quad? If this is, well, let's just take this pen as it is. You're going to take this pen and you're going to draw it on the quad, right? This pen as it is, you're going to draw it on the quad so that your drawing on the quad is the size of the quad. What would you need to do? measure the quad, measure the pin, right? And scale. If this is 2/3 of the way up the pin, then you would go 2/3 of the way up the quad to draw this part of the pin. Does that make sense? All right? So how big is the solar system?
Massive.
That's pretty big. Relative to the Earth. Right? The solar system's 30 AU, basically. From the sun out to Neptune. Where is the Earth in that 30 AU? It's Mercury. By definition, the Earth is at 1 AU. So the Earth is 1/30th of the solar system out, right? Does that make sense? And so where would you stick the Earth on the quad?
The 30th of the way.
30th of the way. Right? It's just a scale factor. Does that make sense? If it doesn't make sense, say, it doesn't make sense, because if it doesn't make sense to you, there are at least 10 other people in the room sitting there thinking it doesn't make sense.
It doesn't make sense.
Okay.
So is there, like I was saying earlier, is there somewhere in the book that I'm missing that says the exact spacing of the planets? Because I'm seeing.
It's somewhere, there's a distance to all of the planets is there in the book somewhere. Yes. It may be in a picture, right? It may be in a picture, but it's there somewhere. So,
Do this on like a separate sheet of paper and just draw them, the whole solar system on over the paper.
so, yeah,
I'm not understanding number one at all.
okay.
It's talking about the radius of the sun and it's using scientific method. I don't
Scientific notation.
Scientific notation. I don't understand.
You don't know scientific notation?
I don't know.
Okay. Who else doesn't know scientific notation? Okay.
I'm not gonna lie, when I looked at all of those problems that, for the homework, when I looked at them, I felt completely lost.
That's okay.
Like, I just sat there for like a couple hours over and over,
So-
like, I would get up and come back.
All right.
I felt
All right.
like an idiot.
It is okay to be lost.
It didn't feel okay.
I know it doesn't feel okay, but if you already knew the answers to all the questions, why would you take the class? If you already knew all the answers to all the questions, why would you take the class? It'd be the most boring class in the right?
I just wanted to look at the stars. I didn't think there was math involved in this class.
It is a science general ed, right? So science general ed maps to quantitative reasoning and critical thinking, okay? So, scientific, let's try and get the quad question out of the way before Dr. Schmidt comes in and gets me out. All right. What's the best way to think of this? Suppose the distance between me and the camera, we're going to call the quad. All right? And we've already discussed if the distance, if I'm the sun and the camera is Neptune, right? That's 30 AU. And the Earth is at 1 AU, right? So how far away is the Earth from me, the sun?
Like right next. Oh wait, right next to us.
No, that's right. It's 1 AU away.
Are you the sun?
I'm the sun.
Oh,
That's Neptune, right? So it's 1 AU away. So I would have to divide this into 30 steps, and it would be 1 step. Right? Does that make sense? Mercury would be 0.4 steps. Right? Venus is like 0.6. Mars, 1.4. You know, Jupiter, right?
Saturn.
Not even even gonna try. Right? Most of the planets, though, are just right here. And then Uranus and Neptune are way out there. Right? So it's scaling things up. So it's looking at where all the planets are and just scaling it to that 250 meters.
I mean, I guess I'm just not seeing that in the book as, I'm not finding those distances to scale. Is it something to look up to Google the distance?
You can Google the distance.
I mean, if it's in the book as a question, it shouldn't be in the book as something we should.
I think it's, so I recall it being in the book, but that may be because I recall who knows what, right? I may be recalling it from somewhere else,
Yeah.
and it's not in the book. But you're welcome to Google things like that, right? How far is Neptune from the sun? How far is,
Something that was not created, that was there.
right,
Yeah.
yeah. All right, scientific notation. I really wish I had a pen. I'm just gonna take Word forever and want because I've never used it on the computer. Scientific notation is a way of using shorthand to say, I'm melting white